Stop. Before you open another tab, close another browser window, or scroll through another playlist of 20 different videos trying to understand chemical bonding, this is it. This single video covers every concept, every principle, every nuance of chemical bonding, from the most foundational idea to the most advanced theory. Everything is here. When this is over, you will never need to search for another explanation again. Everything is here. Let us begin, not with a textbook definition, but with a question. A question that every curious mind should ask. Why do atoms bond at all? The universe, at its most fundamental level, is lazy. Not metaphorically lazy, thermodynamically lazy. Every system in nature tends toward its lowest possible energy state. A ball rolls downhill, heat flows from hot to cold, and atoms, when they come close to one another, rearrange themselves. They rearrange themselves to lower their energy. Chemical bonding is simply atoms doing what the universe demands of them, finding stability. An isolated atom is almost always in a higher energy state. This higher state exists before they are bonded to something else. This is the entire engine driving chemistry. The energy released when a bond forms is real, measurable, and consequential. It is the energy that heats your food, powers your cells, lights your cities, and holds your DNA together. Every single time a bond forms, energy is released. Every single time a bond breaks, energy must be supplied. This is not a rule we invented. This is what atoms do. To understand bonding, you must first understand what atoms are made of. You must understand what they are trying to achieve. The nucleus sits at the center. Dense, positively charged, made of protons and neutrons. Surrounding the nucleus is a cloud of electrons. The electrons are negatively charged, occupying specific regions of space called orbitals. The number of protons defines the element. The electrons, especially those in the outermost shell, define the chemistry, especially those valence electrons. Here is the central principle you must internalize. The most stable electron configuration for most atoms is a full outermost shell. For most elements, this means 8. This is the octet rule. Hydrogen and helium are exceptions. They are satisfied with 2 electrons. But for carbon, nitrogen, oxygen, fluorine, and the rest, 8 is the magic number. And atoms will do almost anything. Share electrons, give electrons away, take electrons from others, to reach that state. Now, there are fundamentally 3 strategies atoms use to achieve stability. The first is ionic bonding. The second is covalent bonding. The third is metallic bonding. Everything else, hydrogen bonds, van der Waals forces, dipole interactions, is built on these. Ionic bonding occurs when one atom has a very strong tendency to give away electrons and another has a very strong tendency to accept them. The classic example is sodium chloride, table salt. Sodium, sitting in group 1 of the periodic table, has 1 valence electron. Getting rid of that single electron would give sodium the same electron configuration as neon, a full stable octet. Chlorine, in group 17, has 7 valence electrons. Accepting 1 more would give chlorine the electron configuration of argon, also a full octet. So sodium gives, chlorine takes, and both become ions. Sodium becomes Na+, a cation, positively charged because it lost a negative electron. Chlorine becomes Kl-, an anion, negatively charged. But here is the critical part. Opposite charges attract. The electrostatic force between Na+ and Kl- is powerful, and it does not stop at just 1 pair. In a crystal of salt, each sodium ion is surrounded by 6 chloride ions, and each chloride ion is surrounded by 6 sodium ions in a beautifully ordered 3-dimensional lattice. This is not a molecule in the traditional sense. There is no discrete NaCl unit. There is a vast, repeating ionic lattice held together by the collective electrostatic attraction of billions upon billions of ions. This is why ionic compounds have high melting points. To melt table salt, you need to supply enough energy to overcome all those attractions simultaneously. At around 800 degrees Celsius, you finally can. Electronegativity determines the result. Electronegativity is the measure of an atom's ability to pull electron density toward itself. Fluorine is the most electronegative element. It pulls electrons more powerfully than any other atom. When the electronegativity difference between two bonded atoms exceeds roughly 1.7, the bond is considered ionic. The electron has been so thoroughly pulled to one side that it is transferred. The electron is effectively transferred, not shared. This brings us to covalent bonding, which happens when atoms share electrons rather than fully transferring them. Sharing is fundamentally different. In a covalent bond, two atoms each contribute one electron to a shared pair. That shared pair occupies a region of space between the two nuclei. Both nuclei are attracted to the shared electrons. This mutual attraction is what holds the atoms together. Consider two hydrogen atoms approaching each other. Each has one electron and one proton. When they come close enough, each electron feels attraction. Each electron feels attraction not only to its own nucleus, but to the other atom's nucleus as well. The electrons start to occupy the space between the nuclei. The energy of the system drops. A bond forms. The result is H2, molecular hydrogen, and it is more stable than two isolated hydrogen atoms by 436 kilojoules per mole. That number represents the bond dissociation energy. That number is the energy you would need to put in to pull the two atoms apart again. The length of a bond and the energy required to break it are intimately related. Short bonds are generally stronger. A single bond between two carbons has a bond length of 154 picometers. A double bond is shorter, about 134 picometers, and stronger. A triple bond is shorter still, 120 picometers, and much stronger. More shared electron pairs means greater attraction, shorter distance, more energy to break. This matters enormously. The reason molecular nitrogen, N2, is so stable is precisely because of its triple bond. Nitrogen has a bond dissociation energy of 945 kilojoules per mole, one of the strongest bonds in all of chemistry. This is why nitrogen makes up 78% of Earth's atmosphere. It just sits there doing almost nothing. Breaking that bond to make nitrogen biologically or industrially useful, the Haber-Bosch process for making ammonia, requires extreme temperatures. It requires extreme pressures and is one of the most energy-intensive processes on Earth. The chemistry of nitrogen fixation sustains modern agriculture and ultimately feeds billions of people, all because of the strength of one triple bond. When two atoms of the same element bond covalently, like in H2 or N2, the electrons are shared perfectly equally. This is nonpolar. But when atoms of different elements bond, say hydrogen and oxygen in water, the electrons are not shared equally. Oxygen is far more electronegative than hydrogen, so it pulls. It pulls the shared electrons toward itself. The oxygen end of the bond accumulates slightly more negative charge, and the hydrogen end is left slightly more positive. We call these partial charges, written with the Greek letter delta, D for the oxygen and D plus for the hydrogen. This is a polar covalent bond. The bond has a dipole moment, a vector pointing from positive to negative. We call these partial charges, written with the Greek letter delta. This is a polar covalent bond. The bond has a dipole moment, a vector pointing from the positive end to the negative end. Whether a molecule as a whole is polar depends on the geometry of those individual bond dipoles. Carbon dioxide has two polar bonds, but they point in opposite directions. They point in exactly opposite directions, so they cancel. CO2 is a nonpolar molecule. Water also has two polar OH bonds, but water is bent. The molecule has a V shape. And the two dipoles do not cancel. Water is a highly polar molecule. This is not a small detail. The polarity of water explains why it is such an extraordinary solvent. It explains why it has an unusually high boiling point, why ice floats on liquid water, and why life as we know it depends on it. To understand molecular geometry, we need VSEPR theory, the valence shell electron pair repulsion theory. The key insight is that electron pairs, whether they are bonding pairs or lone pairs, repel each other and arrange to be as far apart as possible. Consider methane, CH4. The carbon has 4 bonding pairs and 0 lone pairs. 4 pairs arranged to maximize distance form a tetrahedron. All HCH bond angles are 109.5 degrees. This is why carbon compounds, the backbone of all organic chemistry, have such predictable three-dimensional shapes. Add a lone pair and geometry changes. In ammonia, nitrogen has 3 pairs. Nitrogen has 3 bonding pairs and 1 lone pair. 4 pairs total, but the lone pair takes up slightly more space than a bonding pair because it is held by only 1 nucleus instead of 2. The molecule is trigonal pyramidal, with bond angles of 107 degrees, slightly compressed from the tetrahedral ideal by the extra repulsion of the lone pair. Water has 2 lone pairs. Water has 2 lone pairs and 2 bonding pairs. The shape is bent with bond angles of 104.5 degrees. The progression is elegant and logical, tetrahedral to pyramidal to bent, each time compressing the bond angles slightly more as we replace bonding pairs with lone pairs. To describe exactly how electrons are arranged, chemists developed Lewis dot structures, a visual notation where dots represent electrons and lines represent shared pairs. Drawing a correct Lewis structure requires you to count all valence electrons, arrange atoms sensibly, form bonds to satisfy octets, and place any remaining electrons as lone pairs. There are exceptions to the octet rule worth knowing. Boron, with 3 valence electrons, often forms 3 bonds. Boron has only 6 electrons around it. It is electron deficient. Phosphorus and sulfur, in period 3 and below, can expand their octets beyond 8 electrons because they have access to d orbitals. Compounds like PCl5 with 10 electrons around phosphorus and SF6 with 12 around sulfur are real and stable. Sometimes, a single Lewis structure is not enough. Ozone is a perfect example. If you draw a Lewis structure for ozone, you end up placing a double bond to one oxygen and a single bond to the other. But experimentally, both OO bond lengths are identical. Both are intermediate between a single bond and a double bond. Truth is delocalization, spread evenly across both bonds simultaneously. We describe this with resonance structures. 2 or more valid Lewis structures that together describe the true electron distribution. The actual molecule is a resonance hybrid, like a blend of both contributing structures. It is real. Delocalization of electrons is not merely a representational trick. It has real consequences. Benzene, the cyclic hydrocarbon C6H6, has 6 carbon atoms arranged in a hexagon, each contributing 1 electron to a delocalized pi system that extends above and below the entire ring. This makes benzene remarkably stable, far more stable than you would predict. The extra stability from delocalization is called resonance energy or aromaticity. It shapes all of organic chemistry, biochemistry, and pharmacology. The bases of DNA are aromatic. The amino acid phenylalanine is aromatic. The heme group in your hemoglobin is a massive aromatic ring. Aromaticity is not just a chemistry concept. It is woven into the fabric of life. Aromaticity is woven into the architecture of your existence. To go deeper than Lewis structures and VSEPR, we need quantum mechanics and molecular orbital theory. Waves, not planets. Quantum mechanics tells us that electrons do not simply orbit nuclei like planets around a sun. Electrons behave as waves, described by mathematical functions called wave functions. Probability space. The square of the wave function gives the probability of finding the electron. These regions are called atomic orbitals, S, P, D, and F orbitals, each with specific shapes and energy levels. Bonding. When atoms bond, their atomic orbitals combine mathematically to form new molecular orbitals. This is molecular orbital theory, and it is the most complete framework for understanding chemical bonding. When 2 atomic orbitals combine, they always produce 2 molecular orbitals. 1 bonding orbital at lower energy, and 1 anti-bonding orbital at higher energy. Energy dictates the fill. Electrons fill molecular orbitals following the same rules as atomic orbitals. Lowest energy first. This concludes Volume 1. The foundations are laid. We move next to the quantum architecture of matter. The stability of a molecule in molecular orbital theory is described by its bond order. The number of bonding electron pairs minus the number of anti-bonding electron pairs divided by 2. A bond order of 1 is a single bond. 2 is a double bond. 0 means no stable molecule forms. This is why helium-2 does not exist. Both orbitals are filled, giving a bond order of 0. This is why O2 is paramagnetic. 2 electrons end up in degenerate antibonding orbitals, and following Hund's rule, 1 goes into each with parallel spins, giving oxygen magnetic properties. Hybridization bridges the gap between atomic orbitals and observed geometry. Carbon's ground state should only produce 2 bonds, but carbon almost always forms 4 equivalent bonds. The explanation is hybridization. The 2s and 3 2p orbitals mathematically mix to produce 4 equivalent sp3 hybrid orbitals pointing toward the corners of a tetrahedron. Geometry is absolute. When carbon forms a double bond, it uses sp2 hybridization, mixing the 2s with only 2 of the 2p orbitals to form 3 sp2 orbitals in a plane, leaving 1 unhybridized p orbital. This unhybridized p orbital overlaps sideways with the p orbital of the neighboring atom to form a pi bond. Triple bonds involve sp hybridization, leaving 2 unhybridized p orbitals for 2 pi bonds. Sigma bonds, which form by direct end-to-end overlap, allow free rotation. Pi bonds, which form by sideways overlap, do not allow rotation without breaking the bond. This is why isomers exist. In 2-butene, the methyl groups can be on the same side, cis, or opposite sides, trans. Interconverting them requires breaking the pi bond, which does not happen at room temperature. It is absolute. Cis-trans isomerism is critical in biochemistry. The cis bond in unsaturated fatty acids introduces a kink that keeps membranes fluid. Retinal in your eye detects light when a bond flips to trans. Now let us talk about metallic bonding. In metals, atoms release their valence electrons into a collective sea that is shared by all nuclei. The cations sit in a lattice, and the electrons flow freely. This explains everything. Conductivity, because electrons move in response to a field. Malleability and ductility, because layers can slide past one another without destroying the bond. C simply adjusts. The precise quantum description is band theory. Discrete molecular orbitals merge into continuous bands. The band containing valence electrons is the valence band. Above it is the conduction band. In insulators like diamond, there is a large band gap. Electrons need too much energy to jump across. In semiconductors like silicon, the gap is small enough that modest energy can promote them. This is the basis of every transistor, solar cell, and microchip, and therefore of all modern electronics. The physics of bonding in solids is literally the foundation of the information age. Humanity understood. Returning to molecular substances, we must discuss intermolecular forces. These determine physical properties like boiling point. The weakest are London dispersion forces, also called van der Waals forces. Dispersion forces increase with the size of the electron cloud. Larger, more polarizable atoms experience stronger forces. This is why iodine is a solid at room temperature despite being nonpolar. It binds. Dipole-dipole forces occur between polar molecules. Molecules preferentially orient, so the positive end of one is near the negative end of another. This orientation gives a net attractive force. Absolute influence. The strongest intermolecular force is the hydrogen bond between H and N, O, or F. It is an order of magnitude stronger than typical forces. Without it, life as we know it cannot exist. It is the glue of life. Hydrogen bonding is responsible for the structure of ice. Water molecules form a hexagonal lattice. This structure is less dense than liquid water, which is why ice floats and life survived ice ages. Density. In biology, hydrogen bonding is structural. The double helix of DNA is held together by bonds between base pairs, strong enough to hold the helix, yet weak enough to be unzipped. Information is stored in force. Similarly, the secondary structure of proteins is maintained by hydrogen bonds. Change the pattern, and you destroy the function. This is the molecular basis of many diseases, including Alzheimer's. Architecture. Let us take a leap into materials science. Properties are determined by bonding. Ionic solids are hard, but brittle. Shifting a layer shatters the crystal. Dissolve them, and the ions conduct electricity, power. Covalent network solids take bonding to the extreme. Diamond is the paradigmatic example, an infinite tetrahedral network. There are no discrete molecules. The entire crystal is one giant molecule. Hardness. Graphite is made of the same atoms, but hybridized into flat sheets. Electrons are delocalized, making it a conductor. The layers slide past one another. Same element, completely different bonding. Matter. With enough conjugation, the energy gap shrinks to the visible range. This is the physics behind organic light-emitting diodes, OLEDs. Colors arise from electron transitions in conjugated systems. Light. When you see the red of an apple or the green of a leaf, you are seeing quantum mechanical transitions. Coordination chemistry introduces coordinate covalent bonds, where both electrons come from the ligand, complex. Ligands create an electric field that splits orbitals into groups of different energies. Transition metals are vividly colored. Copper is blue, rubies are red, emeralds are green. The chemistry of the transition. Life. The entire field of biochemistry involving metalloenzymes, the iron in your hemoglobin, the zinc in your DNA, depends on coordinate bonding. We visit finally the frontier where chemistry meets physics. Precision. Computational methods have transformed chemistry, allowing us to calculate bond lengths and predict drug behaviors before synthesis. Screening billions of potential molecules before any synthesis is attempted. Drugs. All of this is one subject, chemical bonding. It reduces to the quantum mechanical truth that atoms achieve stability by arranging electrons in configurations of lower energy. Mastery of the invisible world, universe. The bones in your body are ionic minerals. Collagen is hydrogen bonds. Neurons fire due to ion gradients. ATP stores energy in bonds. Understand bonding and you understand medicines, DNA, and the snowflake. Existence. Chemical bonding is the operating system of the material universe. And now you know it, as a unified, coherent story that stretches from a single electron up to the basis of life itself. You do not need another video. Mastery is yours. Information is complete. Matter is understood. The material universe is yours. Absolute. Complete. Masterclass. Mastery. Complete. Absolute, final. Masterclass, complete. Mastery, final. Absolute, complete. Masterclass, complete. Final.